meeting. 10 to 12 వరకు meeting. 9 to 9 to 10 to முடிச்சறா.
Good morning, Sudarshan.
Morning, Pritesh. Can you hear me?
Yes, we are already live.
Oh, really? Oh, sorry. Pritesh?
Yeah.
I go first, right?
Yes.
So I'm not allowed, I'm not able to share the screen.
No, you should be.
So because somebody else is sharing, so I'm not able to share the screen.
Yeah, I'm sharing it. So once I stop, then you can share. I'll just introduce you guys.
Okay, thank you.
Yeah. Good morning, everyone. Welcome to today's session of India webinar series, Introduction to Computational Drug Design. It is organized by Schrodinger and PCI. I would like to take a moment to acknowledge our collaborators who are supporting us, and also the panelists from JSS and Manipal. I would like to also thank the IT team from JSS for hosting these live sessions. Today we have two talks. The first one is Quantum Mechanics for Drug Design by Dr. Sudarshan, and Computational Biologics Design by Dr. Pritesh. During the course of the presentation, if you have any questions, feel free to drop your queries in the chat section of the YouTube video. We will have a Q&A session at the end of each session to answer your questions. So without further ado, I would like to invite our first speaker, Dr. Sudarshan, over to you.
Thank you, Shilya. So I hope it's loud and clear and you can see my slides.
Yes, I can see your slides and I can hear you perfect.
Good morning, everyone. So today I'm going to introduce you to quantum mechanics in computational drug discovery. So quantum mechanics is a subject where we use physical theories to explain things at the subatomic level. So when we do the drug discovery, so we try to understand the interaction between the ligand and the protein molecules. But when we look at the molecular level, the interactions are still driven by the non-bonded interactions between the protein and the ligand molecules. So when we speak about the non-bonded interactions, there are two types of interactions which dominate in these non-bonded interaction types. One is weak van der Waals interactions. So that's based on two non-bonded non-particles. When they come closer to one another, they attract each other. So that's weak van der Waals type interaction. Second is the Coulombic type interaction. In the Coulombic type interaction, we have partial charges sitting on each and every atom because of the electronegativity difference between the bonded atoms. So because of that, though the molecule looks neutral, each and every atom has its own partial charge. So this partial charge plays a crucial role in inducing dipole-dipole interaction between protein and the ligand molecules. So that leads to better binding affinity at the binding pocket. So when we look at the docking, or when we look at the molecular dynamics trajectory, so what we try to visualize it, so how these charged particles are interacting with one another. But first of all, how do we know what is the charge sitting on each and every atom? How do we know what is the electron cloud around each and every residue, so that we can calculate these interactions correctly? For that, we need quantum mechanical calculations. So that's what we're going to see, how quantum mechanics is actually used in the background of docking and molecular dynamic simulations, how it can be used in the context of purifying or reducing your number of heat molecules to limited number of molecules, and better understand your binding pocket and also your selected ligand molecules using quantum mechanics. That's what we're going to do today. Okay, so this is the outline of the talk. We have two sections in this talk. Part one, where I'm going to introduce you to quantum mechanical calculations and importance of quantum mechanical calculations. Then brief history. So because it's about 60 years now. In the 60 years, the quantum mechanics have evolved into a very big thing now. So what happened during the course of this 60 years, and what happens in the background in a quantum mechanical simulation. So that's what I'm going to show in the part one of this talk. In the part two, we're going to see so how QM is used in structure-based drug discovery. So that's in molecular docking or molecular dynamic simulations one. And QM in ligand-based drug discovery. So that's when we don't have the when we don't have the protein structure, or when we don't have a set of ligands that are now pre-docked with the selected target molecule. So when you don't have the structure of the protein, or when you don't have the selected number of molecules, so how you go about designing your ligand-based approach using quantum mechanical simulations. And then finally, understanding the organic molecules using quantum mechanics. So what are all the things that we can predict using quantum mechanical simulations for any given organic ligand molecules. So these are the two parts which I'm going to discuss today. Let's get started. Okay, so yeah, probably you might have seen this one already numerous times. So Schrodinger is a company which produces molecular simulation suites for small molecular drug discovery suite. That is kind of what you have been hearing over the last week or so. Then we have biologics suite. I think after this presentation, Pritesh is going to give you an overview of what are the biologics tools that we have and how we can use them for designing antibodies, antigens, and stuff like that. Then we have machine learning and informatics tools, which are kind of used for building mathematical models or QSPR models, QSAR models, using existing data. For the unknown molecules, we can predict the property based on the existing data for the given structures. Then we have, for the visualization, we have PyMol, which is kind of a tool which is used in the the visualization of molecular level materials. And if you look at any of these journals and within the cover pages with the molecular structures, most of the time they come from PyMol. Then we have material science suite, the suite which is used for understanding materials at the molecular level. So in the context of drug discovery, we can still use this material science suite to understand the properties. When we speak about this material science, we have quite a bit of tools that are available within this umbrella. So we have model builders. So the model builders would allow you to build different types of models from polymers, crystals, disorder systems, nanomaterials, organometallics, molecular libraries, which you might have seen in even in the master also. In the small molecule drug discovery suite also, we have molecular library generations. So we have tools for building any different type of models. Why do we need these models? Basically, if you are thinking about formulations, you want to understand how your drug molecule is interacting with your formulations and drug molecule is interacting with its environment, with the other excipients. We need to build disorder systems. We need to understand binary systems to see how they are interacting with one another, firstly. Second, so if you want to understand how this molecule is going to go and penetrate through a skin membrane or a cell membrane. So we want to build again an interfacial model where we want to build a lipid bilayer and deposit organic molecules on top of it and then see their interaction at the top of the surface. Thirdly, we want to understand the packing materials. So how these packing materials are helping in protecting this APA molecules or any other molecules which are of interest. So how do we understand this package material? So for that, we need to build different types of models. So there are different problems that require different models. So we can build any different type of models using this molecular model generations, model builders. Then we have 4 different engines that can do simulations for us. The one, a molecular quantum mechanics engine called Jaguar, so which is going to be the major thing which I'm going to speak today. So Jaguar is an engine which is used for molecular quantum mechanics. So where we treat the molecules in the vacuum or in the implicit solvent environment in the background. So we can consider how this molecule is behaving under given given environment, given background, or what is its conformational phase space, and also partial charges sitting on each and every atom, the HOMO-LUMO orbitals, which eventually means ionization potential and electron affinity. So we can calculate all those things using Jaguar quantum mechanics engine, and also transition states, reaction pathways. That those things can be calculated using Jaguar engine. Then we have molecular dynamics engine, Desmond, which you might have had a separate session for molecular dynamics. Fastest MD engine that is available to us. So we can do MD simulations using Desmond code. And also we can do coarse grain modeling. Coarse grain modeling, I'll explain you a bit in the further in the slides. Then we have automated QSPR and ML engine, so which is for generating machine learning models or quantitative structure property relationship models. So exist based on the descriptors that can be derived from the existing structural information. And then the periodic DFT, which is for building interfacial and surface properties. Mostly it's for the periodic systems like metallic systems. So when you have metal nanoparticles, which are used as drug carrier materials, so how these metal nanoparticles are interacting with the organic molecules at the interface. So that can be understood. Their absorption energies can be calculated. And there's a chemical reaction that is happening that can be understood using periodic DFT engine. So these are the 4 engines which are there in the material science suite. Then you have property workflows. So no, unlike any other software. So what we have here is we have property-based workflows where we can go and specifically calculate certain properties for the given molecular system. So for example, optoelectronic property would give us absorption, emission spectra, the whole reionization energy, electron reionization energy, which may not directly interest to the drug discovery community. But when we speak about thermomechanical properties, that means glass transition temperature and also the mechanical strength of the material, which is kind of interesting property for even for the tablets and also even for polymers which are used as excipients or drug carrier molecules. So we have to understand their glass transition temperature. And then the transport properties like diffusion, as I told you, how they are penetrating through the skin membrane or the cell membrane, that has to be understood using the transport properties. Then spectra, so the model spectra, we can calculate the model spectra like IR, NMR, UV, X-ray diffraction. So we can calculate these spectra using computational tools also. Then the morphology. So when we have APA molecules, and you have APA molecules are, which are kind of crystallized in different polymorphs. So we want to understand which polymorph is more stable and how these polymorphs are going to be dissolved in under different conditions in presence of different solvent combinations that can be understood using the morphological properties. So we have property-based workflows also, which would allow us to directly compare results from the simulations with the experiments. So all these things put together in a beautiful interface is called Schrodinger's Mitchell sense rate. Okay.
Sudarshan?
So now,
Sudarshan?
yeah.
Can you slow down a bit?
Oh, it's fast. Okay.
Yes, there is a comment in the YouTube.
Okay.
Yeah, thanks.
Okay, I'll slow down because this is all introduction. That's why I was going fast. Don't worry, I'll slow it down now. Okay.
Thanks, Sudarshan. Sorry for disturbing.
Yeah. I'll do that one. Okay. So first of all, why molecular level matters. So why do we need to understand things that are happening at the molecular level? Okay, so anything that is happening at the macroscopic level can be traced back to the molecular level or a subatomic level. So for example, if you look at your binding packet, so where a ligand is getting bound to the protein structure. So as I told you, so it's only the non-bonded, most of the time it's only the non-bonded interactions which contribute to the interaction between the ligand and the protein. So which gives us basically the binding energy of the ligand in the binding packet. So when we look closer and closer at each and every atom which is having an interaction with the protein structure, so it's the electron cloud that's sitting on particular atom of the ligand is interacting with the electron cloud of a protein residue. So this allows this if you can understand this effectively for each and every atom in the ligand and each and every atom in the binding packet residue, so then effectively we can calculate the accurate binding affinity or binding energy. So when we download a PDB structure from the PDB database, what do we get is only the atomic coordinates in the 3D space, XYZ 3D space. We get only that particular coordinates. So how do we, from the coordinates, how do we get this binding energy? So for that, we have to apply something called a force field that would allow us to have the right kind of energy, the potential energy for the given molecular system. So when we bring in two molecular systems, one is protein, another one is ligand, together, so between them, what kind of interactions are happening? So that can be explained based on the interactions between them. So we use these beautiful equations, which were derived in the earlier 20th century for understanding things that are happening at that level. But when we look at closer levels, we need to use the subatomic level or the atomic level. So that's where it's very, very interesting. That's why the molecular level matters, because anything that is happening at the macroscopic level can be traced back to the subatomic level. Okay, so these all things of macroscopic level to microscopic level all started with this particular guy, Sir Isaac Newton. So he, during the second wave of Blake, where he was house quarantined, he came up with the Newtonian dynamics equations, which basically explained from the smallest particle known to mankind at that time to the planetary motions. So everything can be explained using Isaac Newton's equation, three equations, new equations of motion. So an object will remain in rest or uniform motion in a straight line unless acted upon by an external force. It's the first law of Newton. Okay, for each and every action, there is a equal and opposite reaction. That's the third law. But the most important law is the second law, which is what we are using in the molecular dynamics simulation. Basically, if we know the position and velocity of the system at a given point, we can predict its future provided the delta T is small. So that's what the Newton's equation, second equation states. So this guy was able to explain anything that is from the atomic level to all the way to the planetary motions using these beautiful equations. Okay, but during his time, there were no electrons, there were no protons, because the smallest particle known to mankind was an atom or a molecule. So that's why he was able to explain things very well. For 200 years, nobody questions, or even today, we don't question. We don't question anything from Newtonian dynamics when we start using things like molecular dynamics or anything beyond atomistic level. But the moment we go to the subatomic level, so which was discovered in the year 1897 with the J.J. Thomson's gold foil experiment. So when he did the gold foil experiment, he was able to find that the 99.999% of atom is empty. So only you have positive core at the center, and then you have you have electrons which are very small in mass, which are scattered around this nucleus, like a planetary systems, like the solar system which we have. That was Bohr's model for the hydrogen. Okay, so these kind of things which were not discovered, and when we go to such a small particle which are having very small mass, they can be treated like waves. That's what de Broglie proved. That de Broglie proved that it can't only be considered as a particle since it has a mass, but it can be considered also as a wave, because its mass is so small, the size is so small. So these particles actually move like or behave like waves. That's what de Broglie proved in 1924, that wave particle duality of the particles at the subatomic level. Then in 1926, Schrödinger came along. Schrödinger was able to explain things at the subatomic level and solve the equation using his Schrodinger's infamous Schrodinger's time-independent equation. So he was able to give a solution for the electron around electron's energy around the atomic nucleus. So that was the Schrodinger's wave equation, which was discovered, which was discovered in 1926. So that's the start of modern quantum mechanical calculations, or model quantum mechanics as we know now. Okay, so this particular conference, which happened in 1927, which is very important point at the start of the new era of quantum mechanics. You can see there are 27 people, out of which 19 are Nobel laureates. Okay, so that guy, that's Erwin Schrödinger, he published his wave equation in year 1927 or 26. So then immediately after that, people started to use his equation, and they try to solve molecular systems using different kind of approximations, because Schrödinger equation cannot be solved completely beyond hydrogen atom. When you have hydrogen atom, we have nucleus in which we have one proton, we have one electron which is going around it. So one-on-one interaction between this proton and electron can be solved using Schrödinger equation. With a paper and pen, we can derive that equation or the perfect solution for the hydrogen atom. But the moment we go to a slightly complex system, so that means when you go to even a two electron system, that is helium, we have a high correlation because of the second electron's presence on the first electron. The vice versa is also true. So we are not able to calculate the exact solution for the helium atom. So just ignore molecular system as of now. Even for the atomic system, anything beyond hydrogen atom, Schrödinger equation cannot be solved completely. So people came up with the different types of approximations. People came up with the different types of approaches to solve come out of this problem. So what they did is, one of that approach is called Hartree-Fock method. So Hartree-Fock method, which uses some kind of approximation to come up with a solution for a molecular system at the subatomic level. Then the Thomas Fermi model, which is another approximation, which came up with the idea of solving. So that's the base for modern day DFT, density functional theory. Thomas Fermi provided us a solution for the solving Schrödinger's equation for the molecular systems. Then we have Born-Oppenheimer approximation, which is again based on the self-consistent field approximation. So that also provided as another way of solving the molecular systems. Then in 1930s, people still further developed more and more method. A couple of them are worth mentioning: coupled cluster method and MP theory method. So these kind of different methods were discovered by different people for solving Schrödinger's equation for the molecular systems. But think about that situation in 1920s and 30s, where they have no access to the computer, because the invention of computer came into picture only in year 1945. So before that one, it was only paper and pen which was used to derive these equations or try to solve the molecular systems. That's why they were not able to go beyond simplest of models that are possible. Then in year 1964, about 20 years after the invention of computer, the Cohenberg and Kohn, so they came up with the theorem. So that is the base for modern day density functional theory. So in 1965, they published this paper on Kohn-Sham equations, which is what we are using in the modern day density functional theories. Okay, so in 1970 was the first ever quantum mechanical engine or a software was released commercially by Gaussian in 1970. John Pople, so this guy, so he got a Nobel Prize for his basis set notations, basis set development. We'll speak about the basis set in a bit. Okay, so in year 1990, Schrödinger came up with Jaguar quantum mechanics engine, which is commercially made available. Now, if you look at it, there are 100 plus quantum mechanics software which are available that can solve the molecular systems based on either Hartree-Fock approach or density functional theory approach or MP theory or even the coupled cluster approach. So depending upon what kind of approach you are taking, you would be getting different kind of properties that can be predicted for the given molecular system. So that's why there are so many theories. That's why there are so many mathematical derivative mathematical equations that are involved in the background of a quantum mechanical calculation. That's where people lose their interest. But if you look at deeply, it's actually all very straightforward. Now with the help of Jaguar, we can really do quantum mechanical simulation with a simple click of a button. Okay, so that's what now I'm going to show you in the next further presentation, down in the presentation. Okay, when you look at the hiring, the modeling hierarchy, so we have to start with the quantum mechanical simulations. So when we do these quantum mechanical simulations, what do we get is the partial charges. We get the degrees of freedom, the energies on each and every degrees of freedom. When I say degrees of freedom, like we have to calculate the two non-bonded atoms, how they are interacting with one another as a function of distance. That's one thing. And then two charged particles, how they are interacting with one another, and to the charges on each and every atom that has to be calculated. That's coming from quantum mechanics. Then the third thing is bond. So when a bond is vibrating in a molecular system, so how much it can vibrate, what kind of energy we have to give for the bond to vibrate, that has to be calculated. And that bond vibrational energy or bond stretching energy actually coming from quantum mechanical calculation. And then we have angle bending energy. So that means a particular angle. When we say methane, we have HCH angle. So this particular angle is 109 degrees. So, but how much it can bend, how much it can move from this ideal angle of 109.5 degree. So when it moves, how much of energy is required to move this, bend this bond. So that has to be understood. So that is the bending energy that has to come from the quantum mechanical calculation. And also the most important thing is the conformational space. When you have a bond around which the fragment of the molecule can rotate by itself. So that is called a dihedral rotation. So that the dihedral rotation also has to be, the energy of the dihedral rotation also can be calculated, has to be calculated for doing molecular level simulations. So that also is coming from quantum mechanical calculations. So once we have all this information derived from the quantum mechanical calculation, we can use them to fit a force field. That force field is usually applied for molecular level simulations. Either you are doing molecular docking or you are doing a molecular dynamic simulation. All the parameter set that we are using at the molecular level is actually coming from quantum mechanical calculation. So once we have that in the molecular level, we can do molecular dynamics or molecular docking to understand the properties at the atomic level. So sometimes even the atomic level is not going to be sufficient because we can't go beyond, let's say, microsecond simulation. So we want to really do longer time, time simulations. For that, people go from molecular level to the coarse grain level. So when you go to coarse grain level, what happens is we can take a set of atoms that are attached to one another and convert them into a bead or a superatom. Okay, a rigid part of a fragment will be taken and then converted into a bead, a superatom, and that beads are connected to one another. That means we are simply reducing the number of parameters that is required at the molecular level in the coarse grain simulations, so that we can do explore the longer time scales and also bigger size. So these kind of coarse grain simulations are used to understand the phase separation or the permeation or the diffusion or penetration of a molecule through a membrane. So that's where the computational chemistry stops, and that's beyond that one we have continuum dynamics or continuum modeling, finite element modeling, where the information can be either derived from the experiments or from this computational chemistry based models. So you can either derive the input for finite element modeling from this computational chemistry, or you can get it from the experimental values to build the continuum models. But in Schrodinger, we do all these three types of models. Now today we are going to concentrate on quantum mechanics. Okay, so when we say quantum mechanics, so when we want to understand or when you want to elucidate the structure of a ligand molecule using experiments, what do we do is we use either a microscope or a spectroscope. So when we use a spectral data like IR, NMR, and mass spectra, we try to come up with a particular structure. So in the simulations, what do we need is a guess structure. So you can give a guessed structure. So then we can do an optimization and try to find out what's its energy, how the electrons are located, and whether this particular structure is kind of energetically favorable or not. That can be understood using simulations. So basically, it's a virtual experiment which we are running in the computer, where we need to have just a guess of the guessed structure of the given molecular system. Okay, so when we speak about the molecular dynamics and quantum mechanics engine. So as I told you, so this bond energy, so that's called Kb. This is the bonding constant which we require. Angle between the three atoms, Ka, this angle constant is required. So when two non-bonded atoms are interacting, we have this Qi, Qj, the partial charges sitting on each and every atom is required. So once we have this information only, we can do the molecular dynamics simulation. For the quantum mechanics, what do we need is just the structure. Once we have the structure, we know what are each and every type of atom like carbon, nitrogen, oxygen. So we know what are these atoms which are connected to one another. Then we try to solve the Schrodinger's equation, okay, for each and every electron in the system. So we come up with the right kind of structure. So without this structure, this is not possible. The molecular dynamics simulation is not possible. That's why quantum mechanics is crucial for even doing molecular dynamics simulations. Okay, as I told you, Jaguar is the engine which is used in Schrodinger for doing quantum mechanical simulation. Okay, so we have, as I told you, there are multiple people developed multiple levels of theories. So Hartree-Fock theory, density functional theory, MP2 theory. So we have all the three theories that can be done using Jaguar engine. And we have this pseudo-spectral approach, which allows us to run much faster than any other conventional quantum mechanics engine. Then we can do TD-DFT, time-dependent density functional theory. So that would allow us to have spectra, the absorption and emission spectra. Then you have structural optimizations, which is what usually we do to find out the right kind of structure for the given molecular system. And then frequency calculations, which is kind of computational IR spectra. Then we have property-based workflow to understand how this molecule would go through degradation, how this molecule would behave under different pH conditions based on the pKa values. So we have property-based workflows to find those properties. Then automated transition state search. So we have a beautiful engine called AutoTS, where if you know the reactant structure and the product structure, we can predict the transition state structure. So kinetic energy barrier required for that particular reaction to happen, that can be understood using the automated transition state search. Then so we have we can treat even the transition state metals. We have basis sets which are dedicated for predicting properties of the molecular system which are having transition metals in it. Then the background salvation effects, PBF and PCM implicit salvation schemes would allow us to have the background effect of solvent in the molecular system. So this all can be done using the Jaguar engine. The Jaguar engine is probably the fastest DFT engine. Also, it scales up really well, up to 12 CPUs. So you can see, so molecular system as complex as this particular molecule can be treated using Jaguar engine. So which used to be very difficult for treating systems that are having beyond 30 to 60 atoms. Now we can treat hundreds of atoms in Jaguar engine, for the density functional theory calculations. So now in the background, what happens during a density functional theory calculation or a quantum mechanical calculation? Okay, so we have to have the structure, a guessed structure, a starting structure. So we can get a structure either from databases, or we can draw them by ourselves. So then we have the structure ready. We have to select certain things before we go on to submit the quantum mechanical job simulation or DFT job. So we have to select something called basis set. A basis set is nothing but a representation of atomic orbitals. So when we have this molecular system, which constitutes so many atoms, so each and every atom has its own orbital. For example, if you take hydrogen atom has one s orbital only. If you take a carbon atom, you have one s, two s, and two p orbitals. So this orbital space has to be represented correctly. So to represent this orbital space, what do we need is a mathematical function called basis set. So this mathematical functions represent these orbitals in the right way. So when we speak about s orbital, which is spherical in shape, which is kind of small in nature, so spherical in shape, so we need a certain number of basis function to represent that s orbital. When we speak about p orbital, which is a lobe or a dumbbell shape, we have px, py, pz in three different directions. We arranged in three different directions. So to represent them, we need some kind of mathematical function. So that is coming under the basis function. So these are atomic orbitals. So now when you have a molecular system, first we represent the atomic orbitals, then we combine these atomic orbitals linearly, then make the molecular orbital. Linear combination of atomic orbitals would happen. Then we will come up with the molecular orbitals. In the molecular orbitals, the electrons will be arranged in the increased energy order. So to mix them and then come up with the order of molecular orbitals where we can place the electrons based on their energy levels. So that happens at the basis functional level. When we do the basis functional is a molecular property. So where we can't change things for each and every atom in the system, whereas basis set is an atomic property. You can give specific basis set for each and every atom. Whereas the basis functional, which is a molecular property, you have to give one basis functional where it would be treated for the entire molecular system so that we can place the electrons in the right increasing order of energy. Okay, so when we take organic molecules in nature, this particular basis set of 631G double star, which works very well. Why? Because this particular basis set has very good representation for S and P orbitals. So any element that is having only S and P orbital, that would be represented in a right way using the 631G double star basis set. Okay. When we come to organic molecules or the Ligand molecules, which is mostly carbon, nitrogen, oxygen, up to chlorine, there is no d orbital there, so we can safely use 631G double star for that basis set for organic molecules. The same way, when we come to basis functional, there are different types of functionals. B3LYP is a functional which traditionally found to give better structural properties. Then people are looking for structural properties. When you try to optimize the structure, that means we are trying to find out globally preferred structural orientation or structural conformation. So for that, we are using B3LYP, which found to give more close to experimental results for structural details. When people are trying to calculate a transition state structure or transition state energy, so they use something like MO62X, so which is kind of very well known for giving the right kind of energies compared to experimental values. So these are the two parameters which we have to select: basis set and basis functional. The basis set is atomic property, basis functional is a molecular property. As I told you, for organics, 631G double star B3LYP is very much is a thing that is used in the historically. If you look at the literature, about 95% of the time people use B3LYP and 631G double star. Okay, and when we come to a specific calculation type, as I told you, we can do different types of calculation. A single point energy calculation is a calculation for the given molecular system. What is the current energy? So if the structure is coming from crystal database or crystal structure, so we don't need to optimize it because we know that is the structure which how it behaves in the crystal itself. So we can do a simple single point energy calculation for the given molecular structure and calculate the partial charges or any other property of interest. Optimization is involved when we draw our own structure. We don't know what is the preferred orientation or conformation of the molecule. So then we need to do an optimization process where we try to find globally minimized energy conformation. That means that is the preferred structure for the given molecular system. So that's optimization. Then we have torsional scan. So that would be required for fitting force field parameter, which we spoke earlier. If you want to run a molecular dynamics engine, we want to calculate the degrees of freedom like bond angle, bond dihedral. So we want to do this scan to understand how much of energy is required to make the rotation possible, so that we can define that energy for the force field torsional scan. So that kind of calculations can be done. There are other calculations, but these are the three important calculations. Then specify desired properties. When we do these calculations, we can also calculate the properties. For example, ESP charges, as I told you, the partial charges. Okay, so then the surfaces, the molecular surfaces, homo-LUMO orbitals. Okay, so that can be understood. And ESP surface also can be calculated. So these are the specified properties. Then specify other options. That's kind of what kind of details we want to print in the output file, that can be specified. That's just a few options. So, but the important thing is when you have the structure, you have to select the right basis set and the basis functional. In Schrodinger, we have something default which is very well is going to work for your organic system. But if you want to change something, we have huge list of basis set, huge list of basis functional that are available. So how do I select this basis set? Okay, it's not necessarily that bigger basis set is going to give you the better result. Okay, so you can pick up the simplest of basis set, do optimization, take the optimized structure, and then use that optimized structure with a bigger basis set for calculating the right final energy using the single point energy calculation. Because optimization process involves multiple single point energy calculations with the gradient calculations. There we try to reduce the energy of the system so that we can go to the lowest energy possible. So for which it's going to be a time consuming process for a bigger molecular system. We can pick a smaller basis set. Once we optimize it, take the optimized structure, run a single point energy calculation with a bigger basis set. So that's a practical approach for doing DFT simulations. Then how do I select my DFT functional? So if you look at historically, there are different types of DFT functionals which are available. So local density approximation was the one which was initially used by people in the 60s and 70s, but that is not being used now currently for any type of calculation. Okay, so the people use gradient corrected ones, which are used in metallic systems in the material science, gradient corrected ones. So then we have the long range corrected one. When you have very big molecules, we want to see the long range interactions, the long range corrected ones, especially when there are excited states and charge transfer is involved. We have to use this kind of basis set, long range corrected basis set. Then there are non-bonded systems that are present in the system. So it is advised to use the posteriori corrected one. So when you have two molecular systems in your input, so you want to understand the non-bonded interactions between them. So non-covalent interactions. So that can be done using the posteriori corrected one. The hybrid ones, which is a combination of all the three gradient corrected, posteriori corrected, and the long range corrected ones, they tend to give very good results for structure and energy. These are general purpose functionals. So that's why you can see B3LYP 631G double star, which is being used for most of the DFT simulations. Okay, so now when we go into molecular docking, so where we try to find a key that can unlock the protein structure, or that can specifically tightly bind to the given binding packet at the molecular level. So when we look at this interaction between a ligand under the protein, so there are different types of ligand interactions that dominate. So we have pi-pi interactions, pi-cation interactions, hydrogen bonding interactions, okay, salt bridge trade-off type of interaction, dipole interactions. All these are non-bonded interactions, and each and every interaction can contribute from 1 to 5 kilocalories. So if you want to understand these interactions, we want to find out these interactions in the right way. So what do we need to do? We have to have some kind of force field that defines our system in the right way. Okay, when we speak about the force field in Schrodinger, we have OPLS3E force field, so which represents this bond, angle, dihedral, and everything. But the most important part is this non-bonded part. Okay, because we have non-bonded interaction between the ligand and the protein, so that has to be derived from this non-bonded part. We have these two terms, epsilon and sigma, which represent the van der Waals type interaction, Qi, Qj. These two charges, which represent the Coulombic type interactions. If these interactions are represented correctly, then we will have the right kind of binding affinity. If you look at historically, 1970s, first ever protein simulations came into picture. So from that day onwards, people started to optimize force field parameters for protein structures. Okay, when we have protein structures which are made up of 20 different amino acids, for these 20 different amino acids, people parameterized force fields. There are different force fields which parameterized, by different groups around the globe. So we have CHARM, we have AMBER, we have OPLS. So all these different force fields which represent protein structures effectively very well. Okay, when it comes to organic space, if you look at historically, again still 1980s, it was peptidomimics which dominated the drug discovery space. So peptidomimics, people thought the proteins are made up of amino acids. If we can send a small protein or peptide, small peptide into the protein structure, which has the same kind of chemical environment, so they will have better interaction with the protein. So that's why people started to design small molecules that are based on peptidomimics or peptide chains, small short peptide chains. But in the 1980s, the interest started to turn towards small organic molecules other than peptides. When it started to turn towards other organic molecules, these force field parameters were effectively not applicable to new kind of chemical environments that are coming in the new kind of small molecules. So people try to re-optimize these force fields, and that is still happening. Even today, people are trying to re-optimize the force field so that they can adopt all the chemical space that are possible in the small molecular library. We have 10 to the power 60 molecules, small molecules that are possible. So 10 to the power 60 means we have a really huge amount of chemical environments. So to represent all these different chemical environments, we have to have right kind of force fields. All this information is coming from quantum mechanical calculations. Okay, so what happens in the background? So that's what we have to understand. If you look at this particular molecule, so carbon, nitrogen, carbon, carbon, these 4 atoms, if we consider these 4 atoms, and this bond between carbon and nitrogen, this bond has some kind of dihedral energy. So this torsional energy, which allows this benzene ring to rotate around this carbon nitrogen axis. So this rotation energy in OPLS 2005 or in the free OPLS, you can see that's represented by this red curve, okay, which is around 3.5 kilocalories. But quantum mechanically, the energy for that one is 1.5 kilocalorie. So now in OPLS 3, we have the right kind of representation for that dihedral angle. So we can have right kind of dihedral energy. So consider this environment where this molecule is sitting in a binding pocket, and if this particular benzene ring, if it rotates a bit, it can have a pi-pi interaction with the neighboring residue. But now the rotation requires 3.5 kilocalorie energy. So 3.5 kilocalorie energy is very big. So it's not going to rotate. That means the pi-pi interaction is not going to happen. Whereas in reality, it is actually 1.5 kilocalorie. If you have the right kind of representation of energy, this rotation will eventually happen. Then we will see a pi-pi interaction. So if your force field is wrong, you're going to miss out some interactions, which is going to lead to a wrong calculation of binding energy. Okay, so for protein structures, everybody can produce the right kind of results. But when it comes to small molecules, we have to be extremely careful. The force field which you are using is the right kind of force field. That's why in Schrodinger we have force field builder. Okay, in case if we don't know that particular force, particular degree of freedom energy, we will run on the fly quantum mechanical calculation and fit the force field parameter for the given molecular system. Force field builder would allow you to do that one. But don't worry, Schrodinger's OPS3E has 95% of chemical space coverage. So any environment that you take, basically it covers about 95 to 96% of time. You will be able to find the parameter set which are there already in the system. Hundreds of thousands of dihedral energies are there in OPS3E. So that's an advantage of using a more sophisticated force field. So how this force field came into picture? It took 3 years for 75 scientists to develop use based on QM calculations. So they use QM calculations to fit this force field environment. You can see even in presence of solvent and stuff like that. So they come up with the right kind of force field parameters. So in presence of solvent, in absence of solvent, even the partial charges would vary. So here is a partial charge problem. Okay. So if you look at these 5 systems, which are now minimized using 5 different cases. Here you have force field A is applied. Here you have force field C is applied. Here you have OPS3E. Here you have OPS 2005, and this is coming from density functional theory. You can look at it, the more or less the energy, the charges are looking same. The different colors represent different charges. Okay, so basically the red means highly negative, highly positive, highly negative. The green means positive. Okay, blue is positive. Green is somewhere in between, and the orange is somewhere between red and green. Okay, so all of them are having same kind of environment. But if you look closely, this is favipiravir. Okay, the molecule that is currently being used for treating COVID-19. Okay, so this particular molecule is now active because of this particular fluorine atom which is present in the system. Okay, if we remove this fluorine atom, this looks like a regular molecule or a fragment of a molecule, right? Ligand molecule. But this fluorine atoms makes it more interesting, and it's making it more potent. This fluorine atom, if you look at the partial charge sitting on this fluorine atom, here in the force field A, we have minus 0.25, force field C minus 0.25, OPLS3E minus 0.191, OPLS 2005 minus 0.112, OPLS DFT density functional theory gives you minus 0.191. So which is kind of very close to OPLS3E. So that's why you have to do, when you have millions of molecules, you won't be able to do DFT calculation for everything. But when you have a handful of molecules, you can do a simple quantum mechanical calculation and try to see whether the representation of charges are correctly given in your force field, or the force field is giving the right kind of charges for me. So the docking score which I'm calculating, or the binding energy which I'm calculating, is a valid one. So that can be validated by simply running a small DFT calculation, which won't take really long time to do in Jaguar Engine. Okay, so that's why your force field has to be accurate. If you're using Schrodinger, you don't need to worry about it. But if you're using any other force field, you have to be extremely careful that these partial charges are represented correctly. If not, you can run a simple DFT calculation and understand whether this force field is working for me or not. Okay, so people complain that I'm not getting when I do the redocking, I'm not getting the crystal pores. This is because your force field could potentially be wrong. So you have to re-optimize your parameters for the force field. Then when you do the docking, you should be able to reproduce experimental results in the simulations also. Okay, so and curious case of metalloproteins, when you have metalloproteins where metal atoms are present in the protein system, and also metal atoms when they are in the vicinity of the binding pocket, you have to be even more careful. Again, glide is very good in handling this kind of metalloproteins. And also if you feel that you need more sophisticated answer, we can run QM polarized ligand docking, where QM polarized ligand docking would allow you to have re-optimize the partial charges on the binding pocket, so that we can calculate the docking score in an effective way. So you can see the glide is kind of very much comparable with the QPM, QMP, quantum polarized QPLD, quantum polarized ligand docking. But if you feel that the metal is playing a crucial role in your binding pocket, so normally people delete the metal atoms and do the docking. That's absolutely wrong. So when you have metal atoms in your system, you have to reparameterize your force field using quantum mechanics and then redo the docking. So again, we have an engine for that one, quantum polarized ligand docking. So which allows you to calculate the partial charges again and redo the docking. Okay. So when it comes to covalent docking, which is mostly the case now, because people are trying to do covalent binding of the ligand with the protein structure. This bonding can be either reversible or irreversible. But if you look at the cancer treatment, modern day cancer treatment, or even the coronavirus situation, people are trying to do this covalent inhibition. So when we want to do covalent inhibition, there are so-called warheads which are used for making a chemical bond between incoming ligand and the residue of a protein. Okay, so these are examples of warhead. So which warhead to choose, that would decide that would give you the right kind of covalent binding or wrong kind of covalent binding. So we have to understand the covalent inhibitors interaction with the protein structure. So what kind of reaction is happening? So to understand this one, we need to have two energy barriers. One is kinetic energy barrier, which would tell us what is the transition state structure, how much of energy is required for this reaction to happen. Second is thermodynamic energy barrier, where we want to know that the reaction is going to be spontaneous or whether we need to provide some kind of external energy to drive this reaction. Okay, so delta G one and delta G kinetic, delta G thermodynamics. These are the two values which has to be calculated. Again, using quantum mechanical calculations, using DFT, we can calculate both of them. We have panels for running both the calculations for the transition state search as well as the delta G for the thermodynamics. So we can you can see we can compare it for the different warheads and provide you with a right kind of warhead that can provide you effectively good covalent binding between the ligand and the protein structure. So that can be understood using simulations, using quantum mechanical simulations. So these are the examples in the context of structure-based drug discovery. When it comes to ligand-based drug discovery, people use QSAR, quantitative structure activity relationship, right? So we try to relate the intrinsic properties of the given molecular system, molecular structure with its chemical properties. If we know that one, then come up with some kind of biological property. It's mostly the activity. So we try to relate activity to the any known property of the given molecular system, so that we can come up with a mathematical equation that would give us a model. So we can apply this model to unknown molecules and find out or guess whether this molecule is going to be active or inactive. That's QSAR for you, right? But now in the last decade or so, people use QM-based descriptors for this particular QSAR calculations. So HOMO-LUMO energies. So again, effectively, they are going to give you electron affinity and ionization potential. HOMO is highest occupied molecular orbital. So that means that's where your highest level energy electrons are sitting. If you want to eject electron from that molecular system, you have to eject it from HOMO. If you want to place an electron into the molecular system, that is going to happen in the LUMO, lowest unoccupied molecular orbital. So that's your electron affinity. So if you want to calculate the electron affinity or ionization potential, you have to have the HOMO-LUMO. Then the multipole moments. So how the electronegativity differences between the atoms are going to give the dipoles or quadrupoles or octupoles. So which is effectively leads to electrostatic potential, the partial charges. What kind of partial charges are there, which area is dominated in the partial charge, okay, which area is hydrophobic. So those things would be understood from the molecular, from the atomic level context using this particular descriptor. Why these descriptors are crucial? Because as I told you, in the binding packet, it's only the non-bonded interactions which define your binding affinity. If you don't know the protein structure, if you're building a QSAR model, these particular descriptors found to give right kind of models, or models which are much more accurate than traditional conventional descriptors. That's why we can use QM engine to, again, molecular material descriptors. With a single click of a button, we can generate it for hundreds of thousands of molecules. We can generate this descriptors using Schrödinger's material science tool. Okay. Now, when it comes to understanding ligand molecules, I have a ligand molecule. So I'm an organic synthesis guy. So I have I do the organic synthesis, and then I want to understand the docking part. So which is done in the docking tool. I want to understand more about this organic molecule. How do I understand more about this organic molecule? So when we take this organic molecule, we can put it in a different solvent and optimize them. Then find out active reactive site. When there is an actrophile coming in, where it is going to attack in this molecule. When there is a nucleophile coming in, where it is going to attack in this molecule. Potential reactive sites for the given molecular system that can be understood. Then finding the weakest bond. If this molecule is going to go through a degradation process, which bond is going to break effectively? So what kind of fragment can come out of it? So that is finding the weakest bond in the backbone, or in the molecular structure, in the side chain. Then calculate pKa value. So the effectively pKa value will tell us, when I put this molecule under different pH conditions, how this molecule is going to behave, whether it's going to take up a hydrogen, it's going to donate a hydrogen, how this molecule is going to behave under different pH condition. That can be understood using pKa values. So we have 3 different panels which can effectively give you these 3 different values that would allow you to understand more about the given ligand system or molecular system than any other experiment that can provide you the details. These all things can be done within a day's time, so you can have a complete understanding of your molecular system or the ligand molecule. Okay, to summarize, QM plays crucial role in defining force field parameters in effectively all our molecular dynamics and molecular docking calculations depend on how much of a time was spent on fitting force field parameters using the QM calculations. Torsion sampling and partial charges are the 2 parameter sets which play a crucial role in finding the binding affinities. If you are using OPLS3E and a glide, then you don't need to worry about it. If you are using anything else, please make sure that you have the right kind of torsional sampling and right kind of partial charges for the given molecular system. Then when it comes to QSAR for ligand-based drug discovery approach, we have very good descriptors which from the quantum mechanical calculations, which would effectively allow us to have the right kind of models, QSAR models for molecular systems. Then reaction energy barriers, which plays a crucial role in the covalent docking, covalent inhibitors. Okay, so we can find out what kind of warhead would be useful for you using simple quantum mechanical calculations. Then effectively you can use DFT simulations to understand also the entire properties of the molecular system under different conditions, so that you have a complete picture of how the ligand is going to behave under different conditions. So those are the things which you can do using quantum mechanics in the context of drug discovery. The same tools can be used in completely different context, in different environment, different industry. But in the context of drug discovery, computational drug discovery, these are the fair points that we can make using quantum mechanical calculations. This is where I stop. If you have any questions, I'll be glad to answer your questions. Thank you. Over to you, Sylvia.
Thank you, Dr. Sudarshan, for that presentation. We have time for a few questions. As a reminder to all of you, if you haven't submitted your questions, please do so, and we will get them added to the list of the questions that we have. So the first question that we received is, can this material science suite be used like a computer-aided design program to design an immobilized enzyme/nanoparticle sensor plus the substrate material itself from the molecular level upwards?
Yep. So there are, okay. Single word answer is yes, but it is a complicated process. Okay. So what we discuss here is a multi-level problem. So when we speak about the nanoparticle interaction, so we have to build a nanoparticle model and then try to see at the surface of this nanoparticle how this interaction is happening with the enzyme. That's first part. Second, the enzyme's diffusion in itself, that would be the second level of problem. So where we can try to understand how this enzyme is diffusing through the membrane, or or diffusing through the membrane or interacting with the membrane, that can be understood using a coarse-grained approach. Again, we can do that particular part. Then the third part, which would be how it is interacting with the system, so that can be modeled separately. So we have to break this problem into different molecular level problems, and then individually we can calculate their behavior and the mechanisms. Yes, we can do that.
Thank you. Moving on to the second question. Could you please elaborate on quantum espresso tool set if possible?
Yeah, so quantum espresso, which we didn't discuss here. So quantum espresso is an engine which is used for periodic density functional theory. So when we come to metallic systems, okay, when we come to metallic systems, when you consider, no, when we come to metallic systems, we can't simply take a single nickel atom and consider that as a nickel, nickel material or nickel metal. We can't. The same is true for copper or gold, because they would never exist as a single atoms. Whereas when you take an organic molecule, you can take a single organic molecule that would be the representative of all the organic molecules that are there in the beaker. If you take 1 liter of benzene, one benzene is a representation of all the benzene molecules that are there in the particular bottle. But when you take a one single nickel atom, that nickel atom is not a representation of all the nickel atoms that are there in the surface, because depending upon the crystal surfaces, depending upon its environment terminations, this nickel is going to have a different property. So that's why when it comes to metal, we have to treat a periodic systems. That means we have to build a system that's expanded in X and Y plane continuously. So when we want to do that system, quantum mechanics has a restriction of 300 atoms or close to 300 atoms in the molecular level systems. So we can't go beyond that one. So we can't build periodic systems. So people have to come up with some kind of approximation. So they came up with the approximation called periodic density functional theory, where we don't treat core electrons, we treat only valence electrons, which are involved in the reactions or which are involved in the interactions, the valence electrons, so that we can build a model which is expanding in the XY plane periodically, build a model of this surface or interface where we can understand this metallic particles interaction with the incoming organic molecules or incoming another metal interaction. So metal-metal interactions. So for that, we use quantum espresso engine. The quantum espresso engine is used for understanding metal organic interactions in the context of computational drug discovery. I hope it explains. If you need more details, please write to me. We can have a separate discussion on QE.
Right. I don't know if you have already mentioned your email in the slide.
Yeah, I'll give you my email address in a bit.
Yeah, so anybody who has any questions about the QM part or this presentation in particular, you can always write to us at ddcourse@schrodinger.com, and we can pass it on to Dr. Sudarshan. So the next question is, how does Jaguar perform when given to do approx 100 nanosecond simulation of the nitrogenase iron molybdenum cofactor protein complex under in vivo conditions when all parameters included, assuming that you have sufficient hardware? The person says that they're asking this question because it is considered as a good benchmark for QM simulation software.
Well, 100 nanoseconds, I don't think we can do any nanoseconds. We don't do dynamics in quantum mechanics. What we try to do is we try to do the optimization simulations. So we try to find out the what is the most favorable, energetically favorable conformation or orientation between the molecules in the given system. So there is no time here in the quantum mechanical simulations using Jaguar. So when we speak about a molecular system as big as 300 atoms, even with the metal atoms, if you have sophisticated computer, we can put it in a 16 CPU. Let's say even with a metal atom, 300 atoms, we can do it in overnight. So that's how good it is. And we have now even accelerated methods to do these things in a quick span of time. So any simulation that I ran in Jaguar, the maximum time which it took was 36 hours. So that's kind of very fast. Even for a very complex system with 300 atoms and all, it ran for 36 hours. That's it.
Right. I mean, the person is asking about nitrogenase, which is very, very big.
Yeah, upper limit of number of atoms is 300 atoms. Yeah. So we can't go beyond 300 atoms because, as I said, we have to solve it for each and every electron in the system. right? When we treat each and every electron in the system, when you go beyond 300 atoms, which is already approximately about 2000 electrons, so you would require very big amount of memory, computer RAM, which is not possible even in the modern day standards. And also, again, the scaling is not going to be effective. It's going to take really a lot of time for solving it for very, very big systems. But anything below 300 atoms, you can effectively do it.
Right. I think to add to that, Jaguar is one of the fastest, if it is not the fastest in the industry. Yeah.
Yes.
Thank you for that answer. So I did receive a lot of questions.
Shelvia,
Yes.
sorry to interrupt you. There is a follow-up question on the nitrogenous one. The person is asking if the quantum interactions in it can be simulated. Like it's essentially a QMMM approach, I think.
Yep. Yeah, QMMM approach. Yeah, definitely we can do QMMM simulation. So we have a tool called QSAR. Unfortunately, I didn't have time to mention about that one. So QMMM simulation, where we want to treat the core in QM and the rest of the systems in molecular mechanics. Yeah, we do have a tool called QSAR where we can treat the system in both QM and also MM regions. Again, here we are not using dynamics. We are trying to do the minimization at the binding pocket in presence of the background effect of the molecular protein environment, molecular mechanics environment. So we don't do dynamics even in the QMMM simulation. We do the minimization.
Thanks, Darshan. Go ahead, Sylvia.
Thank you, Dr. Sudarshan and Dr. Kaushik for bringing that into our notice. So I did receive a few questions about licensing and hardware part. So I will be going over all of those in the end of the session. So after the second presentation, because it does overlap with some of the announcements that I'm supposed to make today. So I'll just skip those, but I will keep them, keep a copy of all these questions so that I can make sure that I answer all of them. Moving on to the questions related to this presentation. The next question is, what are some of the important software used in QM? I think they're asking what are the
well, there are quite a few of them. Gaussian is one of them. Gaussian is the one which is kind of traditionally being used by a lot of people. But as I told you in Schrodinger, we have Jaguar and quantum espresso. Jaguar is for molecular quantum mechanics. Quantum espresso is for periodic quantum mechanics, periodic DFT.
What are some of the basic sets and the functionals that are generally used for small molecules?
Yep. As I told you, for organic molecules, it's 631G star star. The people use star star plus plus. You don't need the polarization. Actually, you can use 631G star star. That's the basis set. And basis functional, if you are looking for structural properties, you can use B3LYP. If you are looking for energetical properties like transition state energy and stuff like that, you can use MO62X.
Thank you. So what are some of the properties that can be predicted using Jaguar?
Well, as I told you, the reaction dynamics, like we can say whether the reaction is going to be spontaneous or not. First thing. The second thing, we can calculate computational spectra like IR, NMR, UV, X-ray diffraction, band shapes. So these are the things which we can calculate. Then the third thing, what we can calculate is the the kinetic energy barriers and the thermodynamic energy barriers. Then if there are two non-bonded molecules which are coming in, what is the best orientation between these molecules, which way they are going to interact with one another. So that can be calculated. Then atomic partial charges, that's kind of which we discussed. Then non-linear optical properties. So that's again not in the context of drug discovery, but we can predict non-linear optical properties of materials. Basically that's it. Like these are the properties. Anything that is associated with the electronic level calculations can be understood using Jaguar quantum mechanics calculations.
Thank you. We have a question that says, can PK/PD modeling is possible in Schrodinger?
Yeah, okay. PK/PD in the context of what we speak in the pharmacy education. So that can be understood in a completely different context. It's not in the quantum mechanics. That's what I'm going to speak about tomorrow in the formulation studies. So in the formulation studies, how we can effectively try to understand the PKPD studies using computer simulations. That's not today's talk, that's tomorrow's.
Thank you. So the next question is with respect to the hybrid functional default H3 fork exchange used is 0.25. Can we tune this parameter? Better description of the band gap is possible by tuning this exchange parameter in some cases.
Yep, it is. I understand that one, but unfortunately, none of the softwares allow that one. Basically, we have a huge list of basis sets. Like, it's I think probably around in the 60s, 70s. It's huge set of them. So you can use different basis sets where you have different levels of contributions from H3 fork. So then we can benchmark which particular basis set is giving you the right kind of values for given property of interest. So we can try different basis sets, but not changing the percentage of contribution from different functionals. That's not possible yet.
Thank you. The next question is with respect to the slide number 21. How do we know that one particular bond interaction is absent or not included in force fields?
Yeah, okay. So if you are using OPLS3E in Schrodinger, it would comply normally. So in most of the normal organic environment, we have already force field now because we have a release every 3 months. So when there is something is missing, something is being fit by the force field, then it is been automatically updated in the software in the further releases. Okay, so that's why you won't be normally able to see this one. But when you are having some absolutely new environment, it would complain that this particular force field parameter is missing. So then it would ask, do you want to fit a force field parameter for this particular interaction? Then it would fit it by running a quantum mechanical calculation in the background. Okay, but normally for any organic environment, we have very good force fields which are available. As I told you, 96% of the time. That means in the 10 to the power 60 molecules, you can see 96% of the time you will be able to find all the interactions in the existing force field. Hundreds of thousands of different dihedral angles, which nobody else has. None of the other force field has. In case if you are running open source tools, it would also complain that the particular Rickett-Bellman type is missing, or particular torsion is missing, or this force field parameter is not available. This force field parameter is wrong, or you can use 000 value, which is absolutely means that you are allowing it to rotate freely. Okay, but in reality, it has some specific angles which are favored over other angles, which is not going to happen in that particular simulation. That means the dynamics which you are going to do with that kind of force field parameter set is going to be wrong. Okay, that's why you have to be extremely careful when you are choosing your force field. You have to be absolutely certain that it has all the force field parameters for your given molecular system. In OPLS3E, you can go with a certain that it is having all the force field parameters. Even if it is not there, it will allow you to fit that force field parameter. Whereas when you are using any other tool, please be sure that you have all the force field parameters. If not, don't use zeros. That's wrong. Don't give some kind of arbitrary value. Again, that could lead to some kind of potential deformations. Yeah.
Thank you. So I think we have one last question. Do we need to perform QM for metal ligands, for example, a ligand containing a thin atom?
Yes, of course. Yes, of course. So especially when you have metal atoms in your ligand system, I would suggest even if you're using OPLS3, which is good, but still I would run one more DFT calculation to make sure the partial charges which I have is absolutely right.
Thank you. Thank you. That's all for here.
I think there was one question left. I'm sorry if you covered it and I missed it. The question is, what is pseudospectral approach?
Yeah, a pseudospectral approach is to basically increase the speed of the quantum mechanical calculations. So when we use a traditional approach or traditional basis sets, what we try to do is we try to solve the equation for each and every electron in the system, right? In the pseudospectral approach, for the core electrons, there is an effective core potential, ECP, effective core potential, which is applied. The valence electrons are getting more sophisticated basis functions, so that they can be represented in a much more effective way compared to the core electrons. If you take any reactions or any interaction, only the valence electrons are involved in that reaction. The core electrons are simply there. They are never getting interacted with any other things. So that's why we use this pseudospectral method, which allows us to run faster simulations or faster DFT simulations to get the structures or properties in a much more quicker way.
Thanks, Sudarshan. I think that's it. Sylvia, go ahead.
Thank you for that reminder. I'm sorry if I miss any questions, as we received a lot of questions about licensing and other things I might have missed in that crowd. If we miss any question, and if you have any additional question that you're not able to ask here, you can always write to us at ddcourse@schrodinger.com. So I think we are in time for the second presentation. Thank you, Dr. Sudarshan. So our second presentation is computational biologics design by Dr. Pritesh. Over to you, Dr. Pritesh.
Thanks, Sylvia. Do you see my screen?
Yes, I see your screen.
Okay. Okay, so is my audio clear?
Yes, it's clear.
Thank you. Okay, so till now we discussed on various aspects. So on especially focusing on organic molecules, small molecule designing. So we started with the protein preparation or ligand preparation, docking, flexible docking, induced fit docking, covalent docking. We also discussed on ligand-based drug discovery methodology for small molecule design, that is pharmacophore. We also discussed on QSAR and molecular dynamics. Okay, so in the morning presentation, Dr. Sudarshan discussed on quantum mechanics, again, especially focusing on organic molecules. Okay, so in my current presentation, I would be discussing on the biologics, right? Biologics also drug molecules. So it is not always only the organic molecules would serve the purpose as drugs. Even biologics are drugs, right? So for example, I can give you insulin. So insulin is not a small molecule, but it is a drug. Or if you consider a vaccine or antibody, right? So we would be discussing more. So in this platform, the platform in Schrodinger for biologics design is called as Bioluminate. So what all different types of tools we have in Bioluminate for designing the biologics, we will be discussing. So this is the old slide which we had discussed, like PyMol is the visualizer. We will be discussing a lot of details in biologics now. Small molecule discovery tools we came across on material science. Today morning, Dr. Sudarshan presented and discussed on quantum mechanics tool. Tomorrow, he would be talking how these material science tools can be used in formulation design. So there was one very nice question on PKPD and all, right? So tomorrow we will be having in detail discussion on material science again. So now in my presentation, I'll talk on biologics. Okay, so here, while designing this biologics platform, we kept in mind that the interface should be very simple to use. The software tools should be really simple to use. Even if a lab technician who is not very much expert in computational modeling, he should be able to use. Even an expert user, if there is a bioinformatician who is a computational biologist, if he has a lot of experience, he should be also able to use. And it should have a simple platform so that people can communicate, collaborate with each other. So that is what we have kept in mind. And generally, the biologics, the protein, the PyMol is the very famous tool for visualization of proteins and also in the biology field, PyMol was quite famous. So currently PyMol is developed by Schrodinger. So we have implemented same type of visualization tool. If you see the layout, it looks exactly like of PyMol. So here in biologics designing, we go with the structure-based drug discovery approaches. So we have various tools. So it could be modeling, it could be designing new proteins, or it could be identifying the problems or liability in the protein. So for all these approaches, we go with the protein in a simple way, we go with the structure-based drug discovery method. So if the crystal structure is available, we will pick that, we will use that for modeling. If the structure is not available, we will go with the homology modeling. So what type of different tools we have here. It could be antibody designing, epitope designing, it could be library designing, it could be humanization, liability properties like aggregation, reactivity, solubility, right? So these type of tools we use here. So there are nice functionalities, a lot of functionalities present in Bioluminate, starting from antibody designing. There is an automated workflow available where automatically one can choose the template to start template and then go for modeling and loop refinement, humanization. All those things are possible. Then further in protein designing, we have tools like residue scanning, where which can be used for affinity or stability predictions. There is cysteine scanning for protein stability improvisation, protein cross-linking, in silico affinity maturation. So the beauty of this tool is, even if you have non-standard amino acid residues, then those tools also you can use. So for very accurate binding affinity predictions, you can go with the free energy perturbation. Further, for protein liability prediction, the problematic part in the proteins, if you want to identify, there is tools like aggregation propensity prediction, reactive residue prediction, hotspot identification, we call it as, then peptide QSAR, titration curves. With that, you can also identify the isoelectric point, solubility predictions. So all these type of tools we have. In protein modeling, of course, whole set of protein modeling tools we have, starting from homology modeling. It could be sequence alignment, multiple sequence viewer, protein docking, de novo loop modeling, molecular dynamics, chimera model generation. So peptide docking, peptide QSAR. So all these tools we have, and all these tools we have incorporated as a workflow, very simple tool. So we have a lot of workflows. So starting from antibody prediction, then for residue, for affinity and stability prediction, we have tools like residue scanning, alanine scanning. For protein liability predictions, we have workflows like aggregation prediction, reactive residue prediction. Then for in silico affinity maturation, we have, which you can use for designing new biologics, new proteinaceous molecule you can design. We also have workflow for enzyme optimization and even for the protein stabilization. So let us go in detail one by one into each of the workflows. Okay, to start with, first is antibody prediction. So antibody is also a protein. So if you have come across the homology modeling, it is the same principle also applies here, but these are specialized protein because the structure is very much conserved here. So if you remember the structure of antibody, it has two chains, heavy chain and light chain, right? These two chains are held in position by disulfide bridges. Then there is a complementarity determining region which is made up of loops. So in the heavy chain, we have 3 loops, H1, H2, H3 loop. And then in the light chain, we have L1, L2, L3 loops. And these are the loop region, or these the complementarity determining region give the specificity for binding with the antigen. So this is the place where the antibody interacts with the antigen or epitope. So out of all these loop, H3 loop is the very important loop. So this confers the specificity for an antibody. So generally here, when we are talking about antibody modeling, we focus more on the complementarity determining region. So even though the whole framework region can be generated, but the more focus is towards generating the structural model for complementarity determining region. So in Schrodinger, as I mentioned, there is a beautiful workflow. There is an automated workflow available where you can generate a high quality structural model for antibody, whether it is double chain antibodies, or if there is a single domain, a single chain antibody structure. For both of the cases, we have options here. In the workflow, automatically, if you have the sequence, automatically the software will recognize which one is the heavy chain, which one is the light chain, and then there is a inbuilt database of antibody structures. From there, it would select the suitable template, and once it identifies the template, then you can go for loop refinement. So for loop refinement, loop structure modeling, there is de novo modeling approach available. And further, for loop refinement, we have a fantastic tool called as P-loop refinement tool, which uses VSGB model, that is variable dielectric constant model. Because of this, the quality of loops predicted by Schrodinger antibody modeling design is of very high quality. So once you predict the structural model for the antibody, then you can further process it. So you can check the you can go with the protein surface analyzer, and you can check what is the propensity for aggregation, or what is the viscosity. You can check with the stability and binding affinity you can calculate, and for that you can go with the free energy perturbation method. So you can go with the CDR grafting for humanization, and further you can do epitope mapping by going with protein-protein docking tools. So there is an automated workflow where you can go with the epitope identification. You can take an antigen and you can analyze how it is interacting with the antibody. So we will go in detail how the protein-protein docking works in next few slides. So it would identify and it would give us the best poses. Further, for humanization in Schrodinger, we have two tools. So there is automated framework replacement, or based on homology, you can bring out the mutation. So these are the two options you have for antibody humanization. The next tool is protein-protein docking. So in case of small molecule, when we went for small molecule docking, so GLIDE when we used, so GLIDE used flexible ligand rigid docking method, right? So in case of induced fit docking, we considered both the flexibility for the protein as well as the ligand. So in Dr. Vinod's presentation, you might have heard how the induced fit docking works. But here, when we are talking about protein-protein docking, now protein is a huge molecule, so it's a big molecule. So there is nothing like one protein is ligand, one protein is receptor. Both are protein. Just for our understanding, I have put it as one as a protein, one as a ligand. So here, considering multiple factor becomes very complicated. So that is why we go with the rigid body docking. So we, based on the potential energy, we shortlist the best models, and that's how the results are displayed. So once you get the protein-protein docking result, you can use, you can analyze the protein-protein interaction using protein interaction analyzer. There is a automated interface which will analyze what type of interactions are present between different types of residues. So whether it is hydrogen bond, hydrophobic interaction, whether it is pi-pi stacking, what is the surface complementarity, is it solvent exposed? So all these type of analysis it would do. So generally in small molecule, ligand interaction diagram would display you all these details. So it is very simple because the interface would be small, because small organic molecule would be really small. But when we speak about protein-protein interaction, the interface would be really huge, and it becomes really challenging to analyze all the interactions. So in such cases, this type of automated tool to analyze protein-protein interaction, it becomes very handy. So how does we really identify the best poses during protein-protein docking? As I mentioned, we go with rigid body docking methodology. So both the protein as well as, let us say, the ligand as well as the receptor is considered as rigid body. So we go with astronomical sampling here. So what is meant by astronomical sampling? So it is something like Earth is revolving around its own axis, and during doing so, it is also going around the sun. So that is called as astronomical sampling. So during the astronomical sampling, we will explore into the power 6 dimension. So like this. So all the surface we will be exploring. So from this, we will save 1000 best complexes based on the potential energy. The lowest energy, 1000 complexes we will save. Then we will go for clustering. So while applying clustering, we apply a 9 angstrom bracketing. So whichever structures are falling within 9 angstrom RMS deviation, we put it into a single cluster. From that, from each cluster, the best pose with the best potential energy will be displayed as the best pose. Okay, so generally there are two types of ranking we considered here. Either we check the cluster size, the number of complexes in each cluster, that is what we count. So either you can go with that, or we will consider different scoring matrix. So this is how the interface looks like. So here we have dedicated workflow. So if you have normal protein-protein docking, you can go with the standard mode. If you are going with the antibody epitope binding, then there is a dedicated mode for that. Antibody specific mode you can go. Even you have option here to generate the multimeric structure. So if there is a dimer, trimer, tetramer, all those things, options you have here. So either you would be able to see, this is how the output of protein-protein docking analysis appears. So here you can see the cluster size, or even the pose energy you would be able to see, or the pose score you would be able to see. So generally we go with the cluster size for ranking the protein. So nowadays you would also be able to see the pose energy, that is based on the potential energy. So if you have some literature information, there is some knowledge based information that there is particular amino acid residue forming an interaction with the second protein's amino acid residue. So if there is any information like based on experimental results or site generated mutagenesis, those things you can apply as constraints, so the quality of the result further improves. Okay, so if you have multiple proteins, protein-protein docking results, then there are nice tools even for analyzing that. So you can generate a protein fingerprint, protein interaction fingerprints. Then even you can generate nice graphs like for cluster size and all you would be able to generate. Okay, the next tool what we have here is workflow for affinity or stability prediction. So here we have tools like residue scanning and alanine scanning. So you can take the amino acid protein, and in that one by one, if you change the amino acid residue to alanine, we call it as alanine scanning. Instead of changing it to alanine, if you change it to any of the amino acid residue, then we call it as residue scanning. So this is how the panel appears. Very simple panel. You can specify which particular amino acid residue you want to mutate and what residue you want to change. You can specify, and once you modify, what is its influence on the different properties of the protein, that you would be able to check here. So it would calculate the influence of modification on affinity or stability or hydrophobicity or solvent accessible surface area. So various type of property it would be able to calculate. So it generates a nice beautiful table like this, and you would be able to see all the properties, and it would also generate a very good, very beautiful graph, which generally you won't see with any other software. And the same thing you would be able to see in the visualizer. So compared to wild type with the modified amino acid residue, how the interaction is changing, how the complementarity is changing. So a lot of property it would calculate. So for binding affinity calculation, for binding affinity calculation, we go with the force field method. We use here OPLS 3E force field, which is the latest generation force field. I won't go into details. We have discussed now several times about the force field. This covers more than 95% of the chemical space. This is the accurate force field available now, which you can use for proteins, nucleotides, or whether it is DNA, RNA. So every case you can use. So here we go with prime MMGPSA methodology to calculate the binding affinity. So here I will show you an example of the residue mutation experiment we had compared with the experimental results. So we took about 19 protein systems, a protein-protein complex system we had considered, and this was a mixture of both normal proteins and antibody-antigen proteins. So normal protein-protein interface also we considered, even the antibody-antigen complexes we considered. And the proteins, these 19 proteins, whatever we had considered, were having a resolution between 1.9 to 2.8. And about 743 mutations we considered. The same 743 mutations were experimentally then repeated. The wet lab binding data was generated, and here we calculated what is the influence of the mutation on the binding affinity. So of 743 mutation, how many we were able to reproduce? So we could see, so here I have two tables. So I have shown separately the normal for protein-protein interface, and for antibody-antigen interface I have shown. So the binding affinity influence we could accurately measure up to the level of 70%, 0.7 for normal protein-protein interface, And in case of antibody antigen interface, the binding affinity accuracy, the correlation was 72%. So with 743 sample, if we are getting 70% accuracy, it is really good results. That is what we can conclude from these studies. In protein liability prediction, we have tools like aggregation prediction, reactive residue prediction, solubility prediction. So all these type of tools we have. So if protein becomes unstable, if proteins gets aggregated, the clear solution will become like this, turbid. And with this protein aggregation, it loses the biological activity. It becomes unstable. So shelf life will reduce. So here we have various tools. We will go into the details. So protein aggregation. So mainly it is triggered by the hydrophobic surfaces. Further, we will go into the details of protein aggregation hotspot further. The reactive residues. So here we have tools for identifying the places prone for post-translational modifications like the oxidation or deamination, glycosylation. So all these type of tools, the post-translational modification where the protein can get modified or get metabolized, we can identify that. Then further, we also have titration curves. So with this, you can identify isoelectric point, and this will help you in predicting the solubility of the protein. Okay, so in all these cases, we first identify the problematic portion in the protein, the residue which trigger the problem. Then you go for reaction, residue mutation, change the residue and try to remove the liability, and then you check whether the protein is becoming more stable or the modification is it increasing the binding affinity, or at least it is retaining the same binding affinity without with removal of the liability. That is what we check. So as I initially mentioned, it is all the structure based tools we use. So here also we are using the same type of approach. For protein aggregation prediction, we have a very special tool called as patch analyzer. So this is a protein surface analyzer. Okay, so the specialty with protein patch analyzer here is it is a structure based tool. So if you see across any other aggregation prediction tools, these are sequence based tools. So here when we are generating the surface, it is not normal electrostatic surface we are generating. This is how when you normally generate an electrostatic surface it will appear, but this is not the case. But we also generate hydrophobic patches. Now for doing this, it will calculate the log p contribution. So residue wise log p calculation it will do. That is why it is unique. So when you generate the surface, it will trigger, it would show you which are the surfaces on the protein are having hydrophobic patches, and it is because of these hydrophobic exposed, solvent exposed regions, the protein gets aggregated. So now if I just identify and show this is the patch, this is the patch, it is really very difficult, right? So if we can somehow quantify this, now just qualitatively, if you display, okay, there is one patch here, one patch here, one patch here, it really doesn't serve. So if we can quantify it, which particular patch is contributing maximum for protein aggregation, if we can identify that, or if we can rank order it, then that is a really that would give us a lot of information. So with that, we would be able to work on which particular residue can be modified. All those things we can check. So here when you run the agri score, in fact it would rank order. So every patch it would rank order. So which particular patch is contributing maximum for the aggregation, that it would say. Not only that, in a particular patch, which particular amino acid is contributing maximum for triggering the aggregation, all these information it would say, it would share. So with that, you can go for then further residue mutation. You can try to modify the residue to polar residues without compromising the biological activity of the protein. So as I mentioned, the most of the tools like currently available tools are Zegregator or AgriScan. These tools are sequence based tools, and these are developed mainly based on beta amyloid sequences. So if you compare the structure, now those are sequence based tools. So if you compare with those sequence based tools with the AgriScore or patch analyzer, you can see the trend is exactly same. So we get the same quality result. But the advantage here is, since it is a structure-based tool, you would be able to check the influence of conformation. So if protein is having different types of shapes or conformation, let's say active form, inactive form, so what is their contribution? So how the aggregation propensity is changing, or if you want to consider like influence of pH, other environment, other solvent influence, all those things you would be able to consider. Even the non-standard amino acid residue, you will many of the time you will, when you are designing a special protein, you will modify the amino acid residue. So non-standard amino acid residues, modified amino acid residues, even if they are present, the Agri score would be able to consider the contribution coming from there. So this would even avoid the biasing towards the amyloid peptide based prediction. So that is the special advantage here. So since it is structure based tool, this is more accurate, and the quality of results are superior compared to any sequence based tools here. Further, for binding affinity calculation, as I showed you earlier during residue scanning, so we can go with the empirical method, that is based on prime MMGPSA methodology, which is very fast. It hardly takes less than 1 minute for prediction. And if you want to go, now this is not a very accurate, even though it is very fast method, so it can give you a trend. But if you want to go with very accurate method, you can go with free energy perturbation method. So here, this is computationally expensive calculation, because this would go in very, it would consider like, since we are considering here molecular dynamics based calculation, even the energy uphill Hamiltonians, the conformational changes, all those things we are considering, the environment influence like explicit solvent, all those things we are considering. It is computationally expensive, but the precision is very accurate. So compared to the experimental results, so within 1 kilocalorie of the experimental result, the error margin you would be able to predict. So within 1 kilocalorie, so even if you consider the experimental result, you would be able to see at least 1 kilocalorie of experimental error. So it is as equivalent to the experiment, we can say. Okay, so the next tool is for affinity maturation. So when we went for small molecule drug discoveries, we discussed about virtual screening, database screening. So if you have a huge collection of molecule, let's say you have 10 lakh molecule, 1 crore molecule, and from there, from that virtual screening, like for example, we discussed on zinc database, we discussed on Asinex or E molecules, even drug bank, right? So different databases we considered, and from there we identified the best molecule which can bind tightly with the receptor. So something equivalent to that in biologics design is called as affinity maturation. Okay, so in case of residue scanning, we discussed about modifying a single residue. With that, we improved the complementarity in the binding surface of the first protein. With the affinity maturation, we are talking about simultaneous multiple modification in the protein, so that whole of the surface of the second protein we are improvising. So that's how we try to design. So here with this, we bring out simultaneous multiple mutations and their influence on the binding affinity stability we are calculating. So at the end of the prediction, you would be able to see the logo file, like in normal experiments, wet lab experiment, how do you see a logo file? The same type of logo files it would generate. So which particular residue in the particular position will have maximum influence on the binding affinity, it would be able to highlight. In the same direction, we have also tools for enzyme optimization. So if you are working on designing of the enzyme, whether it is the ligand designing, so you can improvise the ligand complementarity with the receptor, or if you want to improve the enzymes complementarity with the substrate, both these are possible. There is a nice publication which was published by Schrodinger Research Group. You can refer this publication. This was published in JCIM, Journal of Chemical Information and Modeling. So this is the reference paper. You can check it out if you are interested. So here you can bring out the modification. So you can go for residue affinity maturation, go for the modification. After, once you get the modified structure, go for MD simulation, the substrate enzyme complex, go for MD simulation, check whether the complex is stable, whether the ligand and protein is showing very least RMS deviation, that you can check. And further, you can also calculate the prime MMGPSA for calculating the binding affinity. So if it shows a stable binding with higher binding affinity, you can retain. If that is not happening, again, you can go for a different modification. You can repeat the experiment till you get a satisfactory result. So that is how you can come up with the design of the better proteins. So the next workflow is for protein stabilization. So most of the time, this is the major limitation what we have, the protein stability. So protein gets denatured. The tertiary structure of the protein will get spoiled, or it will get denatured. So to improve the protein structure, so this is the reason protein loses activity, either when you store it or when inside the body. So to increase the protein stability, you can introduce disulfide bridge. So when you introduce a disulfide bridge, it is something like stapling and forcefully holding the protein with the same type of tertiary structure. Now, this we have to do intelligently, such a way that the cysteine disulfide bridge introduction should not produce any stress on the whole of the protein, and it should not even compromise the activity of the protein. So it should not affect the binding affinity of the protein, right? So to do that, we have a very simple tool, very user-friendly tool called as a cysteine modification. So here what it does is, it will recognize, it would identify all those amino acid residues in the protein which can be modified to cysteine disulfide bridge. Okay, so it will scan the protein, and those amino acid residues where the C alpha atom is falling within 5 angstrom of distance, it would recognize those, it would convert them into alanine. Okay, then it would change it to cysteine, and then it would check whether this modification, so any residue which was present earlier, after modifying that residue to cysteine and by introducing the cysteine disulfide bridge, is it creating a stress locally? So in the backbone, is it creating local stress, or is it creating overall on the protein, on the tertiary structure of the protein? So globally, is it also creating lot of stress? That is what it would check. So in the scoring pattern, scoring, when we go for scoring, it would check the strain energy created, and then the best combination of residues which can be modified, and with the less strain, it would list out. So this is how the interface appears. So here you have option. If there is already cysteine available, you can create a disulfide bridge there, bond there. Or if there is a cysteine and you want to modify, you want to consider any nearby different residue, like it is represented as X. So cysteine to X or X to cysteine. Or if there is totally different residues are there, that is XX residue, you want to introduce as a cysteine, you want to modify it into cysteine, that also can be done. So all the different types of modification you would be able to do here. So here it will display the strain energy, and based on that, you can select which particular combination of cysteine modification would be really beneficial. So here is one publication. So this was published in Cell. So here, this was a very interesting story. So they used cysteine disulfide bridge introduction to increase the thermal stability of the protein. So they wanted to crystallize a protein, and this protein was a GPCR. Now GPCR are very difficult to crystallize, right? So these are membrane proteins. These will have 7 transmembrane helix. The moment you take it out of the membrane, it gets denatured, it loses its tertiary structure. So crystallizing GPCR is a big challenge. So to increase the stability of the protein, they went for cysteine disulfide bridges. So they used bioluminate tool. In that cysteine disulfide workflow they used, and they identified which are the amino acid residues can be modified. With that, they could increase the thermal stability, and with that modification, they could crystallize. So this paper, if you are interested, you can go through this publication. So further, we also have, since we are talking about biologics, it's also all about protein. We also have here workflow for homology modeling. So already Dr. Prajwal has discussed in detail about homology modeling. I won't go again in detail. So here we have automated workflow starting from template identification. If you import the sequence, then you can go with the template identification. You have option for bringing out alignment, where either sequence based alignment or fold based alignment you can bring. Then further you can go for building of the structural model. So once you build, you can go for refinement. There is nice protein reports you can generate. Already Dr. Prajwal has explained these things in detail, so I'm not going again into the details. So yesterday when Dr. Vinod was presenting on QSAR, somebody asked, so is it possible to generate the QSAR for the peptides or protein? Yes. So in Schrodinger, we have a very interesting tool called as BioQSPR. So you have here option to generate the QSAR technique. So you can couple it with machine learning model if you have a lot of samples. So generally always the protein predictions, the QSAR is limited because of availability of data. So very few number of data we will have. So if you have large number of data, then the model generated would be of really good quality. So mainly it is QSPR. Okay, it is not for activity prediction. Generally it is for the property prediction. So various properties like solubility or aggregation prediction or viscosity, these type of properties you would be able to predict here. So for generating the QSAR, we have very interesting descriptors. Okay, so there are 4 different types of descriptors we consider. So there are scalar descriptors. So these descriptors consider entire structure. So these will consider like net charges or isoelectric point or the radius of gyration or the dipole moment. So these type of properties it will consider, the whole structural descriptor. Then we also have about 25 of region specific descriptor. So it will consider zeta potential, charges, surface exposure, hydrogen bond donors, etc., hydrophobicity, these type of property it would calculate. Then there are very specific like patch specific descriptor also. We have about 27 of them. And then there is even the shape specific descriptors are there, about 15 of them. So about 100, near around 90 to 100 type of descriptor we have. So with that, we get very accurate results. So you can go with either continuous models, or if you have option for going with the categorical model generation, then that is also possible. So in the continuous model, we have KPLS, that is kernel based least square. So I won't go into the detail. Yesterday in detail, Vinod had explained all these tools. So what is meant by KPLS, what is meant by MLR, right? Different statistics we discussed, principal component regression, or in the case of categorical model like base classification, recursive partitioning. So all those tools we have here. So you can couple it with auto QSAR, which is a tool present in Schrodinger, which automatically generates the model. So here everything is automated, starting from distribution of training set to test set. So, or it could be identifying which is the best descriptor, or identifying the best statistics. So whether it is linear statistics or categorical statistics, so all those things you can specify there. So automatically it will choose the best combination and the best quality models it would give as the output. So here I'll show you an example. So this was published by Teaser Group, Pete Teaser. So they worked on an antibody and they modified certain of the amino acid residues. So in the region between 16 to 27 and between 33 to 42 position amino acid residues they modified. So about 26 data points they had. So with this, what is the influence of this modification on 2 types of property they wanted to predict? Okay, so the first property they wanted to check was aggregation. Now to predict this, they did not go for patch analyzers. We have a separate tool. I earlier discussed with you about the patch analyzer, that is AgriScan tool. So they did not use that tool. So here they went with the QSAR approach, BioQSPR they did. So with the 26 data points, they tried to generate a model. And here you can see these are the top 10 models generated, and you can see the R square and Q square. So the Q square they got like 0.79. So 80% accuracy they could get with the predicted model. Then further, not only for aggregation propensity prediction, they also went for solubility prediction. And even in the case of solubility prediction, you can see these are the best 10 models. So R square was 0.9 and the Q square was 0.76 or 0.77. So 77% accuracy, they could get it. So there is automated workflow. Further, other than these tools, we have other features like protein interaction analyzer. This already I discussed. So here you can analyze all the amino acid residues in the interface, what type of interactions they are making. So after protein docking, if you want to analyze the results to check the interaction, this is an automated tool. So here it would be able to recognize which residue forms what type of interactions, the non-bonded interactions, whether it is salt bridge, hydrophobic interaction, pi-pi stacking, van der Waals interaction. So all these type of analysis. Addition to that, it would also tell you what is the complementarity, whether it is solvent exposed region. So all those things it will display. Then further, we have protein quality visualizer. So if you go for homology modeling or if you generate an antibody structure, then you can use this tool for checking the quality. So Ramchandran plotted a lot of stereo specific tools. We have stereochemical predictive tools we have here. So you can use that. Then already I discussed about reactive residue information. So here it would predict all the post-translational modification like oxidation, glycosylation, deamination. So these type of tools, the residues prone for post-translational modification, it will choose and it will highlight like this. You can see here different spheres like pink colored sphere or violet colored spheres. So these type of tools it will display here. Further, if you are generating a linker, okay, so there are two protein domains and you want to design a protein linker. So that option also we have here. So either you might be working on a carrier protein designing, or you want to attach two proteins together and you want to keep them in particular position. So in all such cases, you can go with this tool, protein cross-link designer. Then we have titration curves. So isoelectric point, you can predict with that. Then very nice multiple sequence viewer we have. So a lot of different types of analysis you can do with that. Even if there is non-standard amino acid residues, modified amino acid residues, even those things can be read by the force field. OPLS3 is very accurate in that case. That is the special advantage here we have. And also we have protein quality reports. So overall, if you see, bioluminate is something like a Swiss knife. So you have multiple tools here, different tools. So you can explore all these tools, and with that you can reduce the number of experiments need to be done. So number of wet lab experiments need to be carried out, you can reduce. Let us consider an example of antibody and epitope identification. Okay, let's say if the antibody structure is not there, so we can generate an antibody structural model. There is a automated workflow where you can design, or you can generate the structural model for the antibody. Once you have the antibody model generated, you can predict the liability, all the problems present in the like aggregation propensity, post-translational modification, all those things you can identify. You can go for residue mutation to remove all those liability. Similarly, if you have an antigen or epitope, if the crystal structure is already there, you straight away you can use it. If it is not there, go for homology modeling. Once you have the structural model, you go for protein docking. So here it is antibody antigen docking. So once you go for docking, you can go for affinity maturation or residue scanning to improve the binding affinity between the proteins. So you can modify the antibody structure so that the affinity increases, right? Or you can modify epitope so that the antibody affinity increases. Then further you can remove the liability, and that's how. So let us imagine earlier you were planning for about hundreds of biological experiments. So all these mutation, whatever you are imagining, whatever ideas you are generating, all those experiments you had to carry out. Now with bioluminate, you can reduce the number of experiments. Only those experiments, the computational results wherein the modification are showing improvised results, the better results, only those type of experiments you can take it. So hardly 5 to 10 experiments in the labs you can carry out, and that's how it would really reduce the number of experiments to be carried out. So with this, I'll stop my presentation. So again, if you have any questions, we will take up now. Whatever questions we have, we can take up. And further, if you have any queries, you can either write to me at pritesh@schrodinger.com, or even you can write to us at ddcourse@schrodinger.com. So I would be happy to take up a few questions now, if there is any.
Thank you, Dr. Pritesh. Yes, we do have received a few questions. As a reminder, again, if you have any questions regarding this presentation, please add them to the comment section in the YouTube video, and we will add them to our list here. So the first question is, second. Okay. Could you please elaborate about epitope mapping?
Here, basically, we go for protein-protein docking. That is how we work on.
Okay, so I'll move on to the next question. Large biomolecular assemblies like aggregates of antibody, for example, tetramers, octamers, etc., can they be loaded in our interface?
Yes, yes, of course. Yes.
Also, they're asking if we can add moieties like fluorescent probes, HRP, biotin, etc., to the molecules.
Yes, all the modified amino acid residues, or the what we say, even the non-amino acid residues, even if they are associated with the protein, everything you can consider.
So these are some of the labels and the dyes.
Everything, any chemical structure, OPLS3 would be able to handle them. So that's not a problem.
Now, there's a general question about the study materials. Is there any handout, any study material where they can read up about this course?
Andrew Leach is the one which we already discussed. Other than that, you can refer our website. So if you register there, a lot of tutorials, a lot of videos we have, training materials we have. So that is what is coming into my mind now.
Yeah. So I think we discussed about Andrew Leach in our Q&A separate session. So yes, I think that is a good book to start with. Maybe we can send like drop a comment in the YouTube so that people can know the name of the book and the author. Also, like how Dr. Pritesh mentioned, we have material online on our website. If you register to a website, if you have a website account, on top you will see a training tab, so you can go to the training tab. There are a lot of videos, seminars, and tutorial. Other than that, I think we already mentioned about the Schrodinger online course. So that online course will also have a lot of reading material. um, they will go through the basics, there will be videos. So if you're interested in that, you can register for that as well. I'll be going over that later also. The next question we can move on to is what is the difference between PyMol and bioluminate?
PyMol is a dedicated visualizer. PyMol doesn't have any calculation tools. It's only for visualization. Bioluminate is the platform where you can do all the different types of biologics calculation. So it is a collection of applications or tools from Schrodinger. So whatever, like we have all the tools for small molecule design, right? Pharmacophore, Prime, or Glide. So like that, we have different workflows in Bioluminate.
Thank you. So the next question is for QSAR modeling, do we need to use experimental values like IC50? Can we go for G score?
What is G score?
I think it means glide score.
See, Yes and no. I'll tell you what is yes, why it is no. Okay. So ideally, the QSAR model, when you are generating, if you are going with the QSAR, that means you are trying to predict the activity. So if you have a experimental biology activity, then the model generated would be more robust. Okay. So the dependent variable prediction accuracy would be really good when you have the experimental results. And when I say experimental result, it has to be in specific IC50, enzyme inhibition, not MIC. Okay, not minimum inhibitory concentration. The direct readout of the enzyme inhibition, if you have, then you get better correlation. Now, nowadays, the technology is changing. So when people are going with the very large database screening, so let's say a new database, there is a huge collection of database like 10 crore, 20 crore molecules are there. If you go with HTVS, high throughput virtual screening, it would take like very long time. So it may take like 6 months or 1 year to finish the screening. So to avoid that, people go with the smart approach. So what they do, they take a sample. So let's say 1 lakh or 50,000 molecule they'll go for docking. So all the diverse molecule they have collected, and the Schrodinger glide is really very accurate. So it can really differentiate active from inactive. So you have docking score or G score, whatever you are saying. So based on these 50,000 molecules, now you can generate a machine learning model. Okay, so with the machine learning model, it is very fast. So you can apply this generated machine learning model. Machine learning model is also a different type of QSAR model. So with that, you would be able to predict the docking score of rest of the molecule. So you can apply that. So the prediction made with the QSAR models are very fast. It really doesn't take much time. So now you can shortlist from 10 crore molecule. Let's say I want to consider only top 5 lakh molecule or 50,000 molecule. So based on whatever result came from QSAR, you can take those only top 50,000 molecule, and then you can go for in detail docking studies. So standard precision or extra precision docking you can go. And that's how very quickly, in a smart way, you can reduce the turnout time. But now if you ask me, can you really predict the biological affinity with that? That is not possible. So this is only to predict the D score. Okay. So we also have a tool called as active learning glide, so which works on this principle. So we take a sample of whole database, and then we predict the binding or the docking score of the rest of the database, and then we shortlist the molecule. There is one more tool called as active learning free energy perturbation. Now you won't be able to get the access. This is only available for commercial. This is for your information I am sharing you. So free energy perturbation is, as I mentioned in earlier presentation, free energy perturbation is the tool which is used for binding affinity prediction. And the binding affinity prediction made for organic molecule is now very accurate. So compared to experimental result, it is within 0.8 kilocalorie of experimental error results you would be able to compare. That means it is highly accurate. You can consider it as equivalent to the experimental result. So you can take the subset first, like how I told you for the active learning glide, where 50,000 molecule we are initially taking and running the glide docking score, and based on that machine learning model how we generate. Same way here you can run the free energy perturbation prediction, but again free energy perturbation prediction, since they are MD based simulation, they would take longer time, but the accuracy of prediction would be very high here. So with that you can predict very accurately the binding affinity. Then the generated machine learning model from these set of molecule, you can apply it on the rest of the database to predict the best molecule. So this is how intelligently you can use it.
Thank you, Dr. Pritesh, for the answers. I don't see any other questions related to the presentation. All right, then. Thank you, Dr. Pritesh, for the presentation and answering the questions, and everybody who has submitted their questions. Thank you for submitting your questions. I think I will just move on to the questions that you have been asking, the general questions. If you just give me a second, I'll just share my screen. Right. So these are some of the questions that you've been asking, and also there could be a question that you ask later. I will also try to answer those as well. So some of the questions that we received are about the software configurations. So we have, like, if you go and try to request for the evaluation through the form that we have sent you, it has the minimum configuration of the computer that is required to run our software like optimally, right? So if you do not have that, just minimum, if you have something better than that, that is absolutely fine. So for example, the person asked if they have i9 with 512 GB SSD. With just this information alone, I can say that this is a good computer and you can go ahead and install the software. Although you have to check the OS and also the graphics card, which is a GPU card. But I think if you have an i9 machine, it should have a proper RAM and uh, like a good graphics card. So I think you can go ahead and install the software on this machine. The next question is, if you do not have the optimal machine, if your hardware is primitive or it doesn't support one of the the required hardware configuration, you can go for the SOC, which is the Schrodinger's online course. I will be putting the link in my next slide, so you can go and register for it. Just a disclaimer that we are still negotiating or sort of deciding on the price, and we will be sending you a discount coupon. So if you would just wait a few days, we thought we can have it by today, but things are a little delayed, so probably by tomorrow we should have this discount code. Generally, the regular price is $350 for students, and I think $475, if I'm not wrong, for non-students. But we are trying to negotiate this one price for everyone. If possible, we'll have a discounted price around. It should be around $150 if we are able to get the discount done. So please wait till you get the discount code. Do not register yet. We will be sending those out through emails. So please have some patience and we will be sending them out. Do not go and register now. Right. So the next question is that you have we sent you evaluation forms, right? And if you have filled these evaluation forms, we will be writing to you to send out the instructions how to install and install and download this software. If you want to download the software and try to install it yourself before getting those emails, I should tell you that you should be receiving those emails by today and tomorrow. You can go to our website. On top you will see a download icon. So when you click on that, you can download the latest release. Make sure you uncheck the workflows because it takes much longer to install. So we will be sending out these instructions. So if you just wait, you will receive an email with the instructions. So the next question is, if you are interested to purchase the software, how should you go about it? So the quick answer is just write to me, shelvia@schrodinger.com, and I will help you out to purchase the software. Okay. So about the hands-on training, the evaluation license, it is completely free. You do not need to pay anything for the evaluation license and the training that you'll be receiving through this course. So all the demo sessions will start, and you will be able to get that training for free as you are doing right now with this course. The only fee which is optional is when you buy the SOC, which is the Schrodinger online course. So the online course is the only thing that where you can pay, and it is completely optional if you want to go for it. It is a very nice course that starts from the basics, and it is self-paced, so you can take it whenever you're free. You will have the access for about 5 weeks. It only takes about 25 hours, 25 hours to complete this course. So whenever you have a little time, you can go and take this course. The discount coupons that I'll be sending you, the discount codes, excuse me, will be only eligible for the upcoming session. So if you want to take it, this session, the coming up session, it will be discounted as you're taking this course. Just because of this course alone, we will be able to give you the discount codes. For any other sessions, you will not be having those codes, so you have to pay the entire fee, which is $350 for the students. Other than that, make sure that you email us with any of your queries at ddcourse@schrodinger.com. If you have registered and if you haven't received any emails from us, you can write to us and we will send you the form for evaluation. Make sure you register for this course. So to register to this course, you have to go to schrodinger.com/dd course. So when you go to this website, excuse me. So when you go to this link, you will see a registration link. Make sure you register. And the other thing is, if you have any other questions, you can always email it to us. For online course, if you want to just know about it, what all is included in it and what all do you get, what are the advantages, you can go and read up about it at schrodinger.com/Schrodinger online learning, with it is hyphens in between. um, for downloading, and also to get the training material, and to go through the conferences, also in order to receive notifications for future events. Please make sure that you register for this account. So this is a website account. You get that on our website. So in order to also to get the Schrodinger online course, you have to have this website account. In order to download a software, you have to have this. So if you haven't done it yet, please go ahead and do it. This is separate. This is not the same as the registration link for the DD discovery course. That is separate. You have to register for that also, and this is separate. This is a website account link where you have this for your lifetime or till you have that email. um, so you can do that as well. The other thing is, we have some exciting talks coming up by our industry partners from India and Europe. The first one is by Syngene on October 3rd. That is a Saturday. We do not have any session this Friday. We usually do not have any sessions on the weekends. That is Saturday, Sunday. But we do have one session only this Saturday. That's an exception, which is October 3rd. I think I went over all the questions. Let me just see.
Can you also elaborate on the time for the talk on Saturday?
If I'm not wrong, I think it starts at 10:30.
Yes, that's right. The talk is from 10:30 to 12:30. And can you also inform them about the Q&A sessions?
Yes, so we also have the Zoom sessions, which are the office hours where you can just join and ask your questions. So which are every Thursdays. The Zoom link is there on the website. So if you go to schrodinger.com/dd course, so this website, the Zoom link, how to join this meeting and the password for this meeting is mentioned. If you can't find it, you can always email it to us. So the Q&A sessions are every Thursday from 4:30 to 5:30.
Thanks, Shelby. And there's one more question for you. Can you just check the chat box?
Okay. Okay. So I have registered for Schrodinger website account on last week, but my account is not activated. So what you can do is you can write to us, or the easiest way is to write to help@schrodinger.com. So they can just activate your account if it is not activated, maybe got missed. So you can send an email from your the email that you used to register. Make sure you also verify your email. So once you submit the request, you will get an email to verify your email on your the same email that you send. So make sure you click on the verifying link, only then it will get activated. Also make sure that you give all your details. So all the details are necessary. If you miss out on your company, your university, if you do not enter that, the account will not be activated. They will be sending an email to you, and make sure that you have verified your email also. So yeah, just write to help Schrodinger for any web account related queries only. For anything else, you can write to us on ddcourse@schrodinger.com. Is there any other question?
That should be it.
Okay. Thank you then. Thank you for joining today. Please join us tomorrow for our formulation design talk by Dr. Sudarshan. And I think that's it from me. Have a great day. Bye-bye.
We can stop the live session here.
Okay.